these last few questions, and I think question 16, 17, 18, 19, they're all in the same category of recurrence relations that don't just directly fall out after integration by parts. You do have to do integration by parts often, but there's little weird algebraic things you got to do in there in order to get out the exact relation that they're after. Okay. So, we have a look at this. Your first instinct should always be to try integration by parts, okay? Even if it doesn't work out, at least you'll learn, okay, I'm gonna have to try something else, okay? So have a look here. Here's your product. So what might you suggest would be a good choice? I'll draw my table up. Where shall I do it? Oh, yeah, I'll do it over here. It's fine. What might you suggest would be good choices for U and dV? What do you reckon? I've got x, and I've got this disastrous thing in here, 1 minus x cubed all to the power of n. Which one do you think would be a better option to choose as u? It's probably going to be this guy, right? The reason why I go for him is because whatever I choose for dv, I have to integrate. I don't really want to integrate that, okay? So I'm staying away from that as far as I can. There's another reason why you might use this as u. As you'll see in a second when I differentiate. What's the derivative? What's d on dx? You got to do chain rule, right? Sorry, that's a bit messy. So you're going to end up with 3x squared, negative 3x squared, the derivative of the inside out the front. But that's not all you get, right? I've just done the inside, so what happens to the outside? You get the n, that power comes down, and then the power reduces by 1. 1 minus x cubed to the n minus 1. Here's our other clue for why this is a good choice for u, okay? That 1 minus x cubed to the n minus 1, surely that's going to be important for our in minus 1 here, okay? Because that's the difference between in and in minus 1. It's just that power. Okay, so the fact that we've differentiated and gotten that sort of piece of the puzzle there, that's a good sign. Okay, good. Now we've just got a simple dv and v. So I've chosen x, which means that v should be equal to x squared on 2. Okay, now you're right to be hesitant when you see this. Okay, because I showed you an example of this before, where you got this kind of scenario. You got these two guys, and I showed you, and I said, this is a bad time to use integration by parts. Because now look at this disaster that results when you get v du, right? It looks like it's going to be terrible, okay? But you've got two things to think about. Number one, think about what would happen if you did it the other way around. Like I said, integrating this is going to be much more difficult, okay? Number two, we're not just doing straight integration. We're doing recurrence relations, okay? So therefore, you can take terms like this, right? And if you can see that they're related to some form of the integral, you can just get rid of them and not worry about trying to evaluate them, which is exactly what's going to happen in a second. Okay, let's try and pull this out. This is my integral of u dv. Okay. So just what is my normal form for integration by parts here? What do I start with? uv minus v du, right? Now, one of the reasons why I'm going to the effort of actually writing this out is because this question is a little bit different to our normal just regular integrals. It's a definite integral, right? And that 0 to 1 is not there by coincidence. In fact, we need that. If you've been going around and around in circles with this question, part of why might be because you haven't resolved the fact that that definite integral is there for a reason. So if there is a 0 to 1 here, okay? That definite integral, those boundaries have to appear over here as well, okay? So for starters, this guy is going to be evaluated from 0 to 1, okay? And in the same way, the other integral we've got over here, it has the same boundary, okay? Okay, good. Now we can actually write this out. What am I going to get? Here's my u and my v. Okay, so this is what goes in these square brackets. X squared on 2, 1 minus x cubed to the n from 0 to 1. Okay, what's my other piece? It's this monstrous thing here, right, from 0 to 1 of, now let's do a bit of simplifying if we can, right? I see a minus 3 over 2. You see that? Minus 3 over 2. Then what's left in terms of the algebra? there's a single n, there's an x squared here and an x squared there. So I think that's mx to the 4. Is that right? And then you get all of this garbage over here. Okay, now, it looks bad. It does, okay? Stay with it. For example, one of the reasons you can know you're on the right track is because you think about what happens to this guy, right? We're going to evaluate him at 1 and then subtract him evaluated at 0, right? But look at what you've got there. When you evaluate this at 1, what happens? He just vanishes, right? Because you stick a 1 in there and it doesn't matter what anything else is, okay? So you get 0, okay? You evaluate it at 0 and the same thing happens because of the x squared, right? So you get a big fat 0 minus 0 over there from that definite integral. That's really, really good. Okay. What happens here? Let's tidy up a little bit. I'm integrating with respect to x, yes? So that means I don't need to worry about anything that's not an x term in here, okay? So for me, that means these guys. Okay, I don't need to worry about them inside the integral, okay? And it'll just be simpler if I can see the integral without them. Double negative becomes a positive. I'll have 3 over 2n, so 3n on 2. Now that right there should be another tick for you, right? It's not arbitrary. It looks very suspicious being what you have to prove, right? So being that there's all this complicated algebra, you need to look for things like this and this that give you clues that you are on the right track and you've chosen the right method. That's good. What's in here? Not to 1. X to the 4. Right, now, we need to do something with this. This is intractable in its current form, okay? But you have some clues as to how you can muck around with it to make it workable, okay? Clue number 1 is that we wanted an in to the minus 1 somewhere over here, didn't we? Okay, because in is, this is in, okay? Now, that means you're going to have an x term at the front and then some number of 1 minus x cubed to the m. Okay? So I've got the 1 minus x cubed to the something, but I don't have an x here. I've got 4 x's, okay? No problem. That's all right. We'll just take one out and deal with him separately, right? So I've got this. I've got the 3n over 2, this gross integral. I've got that x out the front that I need for it to fit in terms of what they call capital I, right? So stick that guy there. And then I've got an x cubed that's left over because I took one out, right? So you got this. Okay, now, if only I didn't have this x cubed here, right? That would be in minus 1, wouldn't it? Okay. So in some cases, this is a very good situation to be in. I've gotten some part the way there. But I'm not all the way there, am I? How can I deal with this x cubed? I have to get him out somehow, right? Now, the easiest way to get rid of that x cubed is to see that, well, the closest thing to an x cubed here is this guy, right? If these two can interact in some way, then I can get him out of the way. I can break apart that integral, okay? So how do I go about doing this? How do I get him to interact with that? Okay. Well, let's see. I'll do it over here. I've got 3n over 2, integral 0 to 1, x. Okay. I want that x cubed to be something like a 1 minus x cubed, right? So if I had a 1 minus x cubed here, okay, and that's going to, you know, play index laws with this in a minute, okay? What's the difference between this and this? There's two differences. I'm off by a constant of 1, and I'm backwards, right? This is a minus, and that's a plus. No problem. That's okay. I can deal with that. I said I was off by a factor of a constant of 1, okay? So if I stick a 1 there, these two will cancel, and I said I'm backwards. So I'll make it backwards, which is the right way around, okay? Just stop and have a look at that for a second, because in some ways that's the hardest step, I think. Seeing that this is equal to x cubed, because it's 1 minus 1 plus x cubed. That's x cubed, okay? That is very hard to see. I think that's the trick of this question, okay? Because I saw this x cubed that was a problem, I wanted it to interact with this 1 minus x cubed somehow, and I pulled this weird algebraic trick, which is just like with your trig identities when you multiply and divide by the same thing and you get a new identity out of it. I've pulled that in here so that I have a 1 minus x cubed now. Okay. So I've substituted that for x cubed. Now I have the rest of this here. Blah, gross. Okay, watch. You know how things get worse before they get better? This is as bad as it gets. Everything from here on in is going to be simplified. See this minus sign in here? This one right here. He's kind of the key now because the difference of two integrals, one integral minus another, I can just break that apart. I don't have a product anymore which I can't separate out. I can just say, here's one integral and here's another, one minus the other. Okay? So what would be the first integral? Well, it's still got a 3n over 2 out the front. It's still from 0 to 1. All right, let's have a look here. Maybe to make it a little bit easier for you, I'll put this x back inside. Watch. X times 1 is x. X times 1 minus x cubed is that. Now, to break it apart, I've got the first pairing, x times that. Okay, so I've got x times that. There's one integral. Done. Finished. Then I do the next one. Starts with a minus, so I better start with a minus, right? But he still has all of this stuff carried with him. He's still got a 3n over 2 out the front. He's still from 0 to 1, but it's not an x anymore. It's x1 minus x cubed. Okay, so that's this pairing. Okay, got two pairings, two integrals, right? Have a look at this here. What is it? That's in minus 1, isn't it? Matches exactly. The only difference is the power. Okay, so therefore I've got 3n over 2 in minus 1. That's really good. Okay, what do I have here? I've got 1 minus x cubed here. I've got n minus 1 of them there. So how many do I have in total? I've got n of them. If I've got n of them, then this is x times 1 minus x cubed to the n. It's exactly this. Exactly that. No difference. That's in. Okay? This whole thing was in, right? And I want a relationship between in and in minus 1. I want in to be the subject. So I'll just rearrange a little bit, tidy up. Let's have two of these over here. Get all your in's on one side, so you got to add. So I've got 3n of them over there, 2 there, 3n of these guys, and I'm pretty much there, aren't I? How many in total? 3n plus 2 of them. 3n of these, and then you just divide. After which you collapse in a heap and think, are you serious? How many marks does this thing work? Okay. Let's just review. What was hard about this question? Many things, right? So for this reason, I would expect this to be like, you know, right at the end of an exam paper, just like it's at the end of an exam, if you were to get such a question. Okay. The first thing that was hard is that it looks like the form resists integration by parts. It looks like it, okay? But if you stay with it, noting this definite integral just makes all of that vanish, right? And then seeing that you needed to get rid of this through this weird trick, okay, the rest of it kind of falls out. Okay? So I think your two pressure points are here and staying with that, being confident that this is going to go somewhere, right, which gets you to here. And then your second pressure point is working out how to resolve this guy. It's almost like a trig identity, kind of, in the way that you have to sort of conjure up, I should add one and take one away and turn the thing backwards so that these two can go together. Okay?